This presentation is the Wister Dam case history where concentrated leak erosion resulted in a dam safety incident. The objective of this presentation is to identify the key factors and clues about possible vulnerabilities important to evaluating concentrated leak erosion. You can then apply these same clues as indicators to guide judgment when assigning more and less likely factors and assessing the likelihood of concentrated leak erosion at other structures. This presentation will cover some background on the dam, the 1949 incident, and an evaluation of concentrated leak erosion for the conditions present. Let's start with some background. Wister Dam is owned and operated by the Corps of Engineers and is located near Wister, Oklahoma. It is essentially a homogeneous embankment dam comprised of silty clays and clayey silts with an average plasticity index of 9, which were found to be dispersive after construction. It has random fill seepage and stability berms upstream and downstream. The random fill berms were comprised primarily of shale and sandstone from the required excavations. Finger drains were constructed over the downstream 2/3 of the embankment to allow for consolidation of the embankment and overburden foundation soils during and after construction. The embankment was built on a shale foundation with no cutoff trench and without a grout curtain. Here's a plan view of the embankment. The Poteau River was diverted through the outlet works, constructed to the right of the old riverbed. The closely spaced dashed lines perpendicular to the center line highlighted in yellow are the gravel finger drains. The finger drains were not placed in the location of the old riverbed because this was the only area where the overburden soils were completely removed to rock. The foundation rock is comprised of moderately soft to moderately hard shale with interbedded sandstone and siltstones. The rock dips about 28 degrees to the north along the longitudinal axis of the dam. The thickness of the overburden in the floodplain ranges from 0 to 39 feet, with an average of about 28 feet. The overburden consists of silty clays and clayey silts with small sand lenses. Wister Dam was authorized in 1938, but the notice to proceed for construction was not received until 1946. Most of the embankment and outlet works were constructed over about 2 years, shown here in plan and profile. This shows the construction accomplished through June 1948. In June 1948, the Poteau River was diverted through the outlet works. Over the next 6 to 7 months, the channel was filled and the closer section of the embankment was constructed. The portion of the embankment shaded in blue was allowed to sit for 14 months prior to reservoir impoundment. The closer section shaded in red was completed approximately 1.5 to 2 months prior to reservoir impoundment. The following slides describe the 1949 internal erosion incident. From January 23rd to the 27th in 1949, 8.43 inches of rain fell in the watershed. On January 28th, the reservoir crested at elevation 493.5 feet, about 50% of the embankment height, and it remained there for 12 hours and then slowly began to fall. 2 days later, leakage was observed in the morning at station 9+09 on the downstream slope, approximately 5 to 10 feet above the toe of the slope. A number of leaks developed later in the afternoon from station 4 to station 10 with an estimated flow of 5 CFS. 3 days later, the leakage volume increased and additional seepage appeared between station 10 and station 14+40. This is a photograph from 1949 of one of 30 or more initial leaks that appeared on the downstream face of the dam at the closure section. The leakage appears to be carrying fine-grained material. The silhouettes of 2 people standing on the crest of the dam next to a car can be seen in the background. Leakage continues to increase, and flow is measured at 18 CFS. The discharge point at station 9+09 climbed to elevation 478, and exploratory drilling from the crest begins. On the next day, a hole appears on the upstream face at the embankment at station 2+12 at elevation 485. Tracing dye exits the downstream face at station 9+09 at elevation 475, approximately 13 minutes later. Crushed rock was placed in the hole, reducing the flow by 1/3. Over the next 3 days, additional upstream erosion channels appear over several hundred feet at approximately elevation 485. Finally, the reservoir level begins to fall below the upstream erosion tunnels, essentially stopping leakage and arresting the potential failure mode development. In the photo on the left, the reservoir is at elevation 488.9 and falling, which is about 4 feet of hydraulic head above the upstream entrance location. In the photo on the right, the reservoir is at elevation 485.8 and falling, which is about 1 foot of hydraulic head above the upstream entrance location. Although the hydraulic head difference has decreased by about 3 feet between the two photos, the leakage appears to increase significantly, indicating the internal erosion pathways are increasing in size. This is a plan view of the area around the old Poteau riverbed where the closure section was placed. The outlet works is located to the right of the old riverbed. The blue dots are located at the downstream leakage exit locations, and the red dots are located at the upstream entrances. It took 13 minutes for tracing dye placed at the upstream entrance locations to emerge from the leakage exits, located 715 feet downstream. That is just under 1 foot per second. Here's the cross-section of the embankment that shows a straight line between the elevation of the leakage entrance and exit locations. This is a 3D problem that really needs to be viewed in plan and profile to really understand. The failure path does not extend directly across the embankment, but was instead likely at an angle, generally following the old riverbed. The accuracy of the erosion pathway shown is not clear. The failure path was never excavated, so it's difficult to be sure what it really looked like. Evaluation of concentrated leak erosion. Here's the typical event tree for concentrated leak erosion. This section will step through each node in the event tree for Wister Dam. Node 1. What is the likelihood that a transverse crack exists in the embankment due to differential settlement? This figure is a profile along the center line of the dam looking upstream. The heavy black line shows the originally interpreted top of rock surface. Some of the overburden was removed, but most was left in place as shaded in green. The light gray, angled dash lines depict the dip of the bedrock. The foundation profile in the red box will be examined more closely on the next slides. The top figure is a plan view of the area where the seeps and leaks occurred. The lower figure is a profile of the foundation downstream in the area of the old riverbed. Specifically, this profile drawing is a log of the sheet piles driven 118 feet upstream of the center line as a risk reduction or intervention method taken shortly after the leakage to the embankment began in order to try arrest the leakage. The foundation stripping line is shown in blue. The old riverbed of the Poteau River is the low spot in the foundation stripping line near the center of the profile, shown in red. The original interpretation of the rock surface on the right side of the riverbed followed the foundation stripping line, now shown in blue. However, the logs of the sheet pile installation show the actual rock surface is deeper. Based on the new understanding of the location of the downstream rock surface, the profile would look like this. Instead of incompressible rock, there was 20 to 30 feet of compressible, silty clay alluvial material left in place. A large triangular area of compressible overburden material was left in place as shown on the plan view. This was verified by exploratory boring hole A that was advanced after the start of the incident in 1949, which showed low plasticity clay down to an elevation of 431. Zooming out, this area with the seeps and leaks is shown in blue, and the internal erosion entrances are shown in red. Examination of the profile along the center line of the embankment provides a better picture of what is causing this flaw. On the profile figure at the bottom, the well-compacted fill of the embankment, shaded in brown, is applying pressure to the soft, compressible overburden material, shaded in gray, as well as the well-compacted fill placed in the old riverbed. The difference in stiffness between the well-compacted riverbed fill and the compressible overburden resulted in a low-stress zone developing and a crack opening up. It is possible that this crack was continuous from upstream to downstream from the start, or only part or most of the way across the embankment, and was ultimately opened up as it was loaded by the rising reservoir level by hydraulic fracturing. Node 2. What is the likelihood that sufficient hydraulic shear stress exists to initiate concentrated leak erosion in the crack? The estimation of initiation of concentrated leak erosion involves both analytical methods and performance observations. This slide shows the RMC Concentrated Leak Erosion Initiation Toolbox output that can be used to inform the likelihood of initiation. The multicolored series of lines are the hydraulic shear stress as a function of crack width for different reservoir levels. For this case history, the reservoir levels of interest range from the peak reservoir elevation of 493.5 to elevation 485, which was the entrance location of the pipes. The rectangular box bounds the estimates of crack width, shown by the red arrows, and the critical shear stress for the embankment, shown by the blue arrows. The critical shear stress can be informed by the RMC erodibility parameters toolbox, and the crack width can be informed by the RMC concentrated leak erosion, crack width, and depth toolbox. The mean refers to the expected value of the critical shear stress and crack width based on the input distribution, and the mode refers to the most likely value or best estimate. From this figure, the reservoir level and crack width needed to exceed a given critical shear stress can be estimated. Initiation of erosion is assumed to occur when the critical shear stress is exceeded. For example, the hydraulic shear stress imposed by reservoir elevation 493.5, the purple line, exceeds the mean critical shear strength and mean crack width, the green dot. The hydraulic shear stress at elevation 492 is about equal, and the hydraulic shear stress at elevation 490.5 does not exceed it. Therefore, based on the mean values, initiation of erosion is not predicted at elevation 490.5, but it is for elevation 493.5. For the best estimate or mode parameters, the blue dot, initiation of erosion is predicted for all reservoir levels above elevation 485 because the hydraulic shear stress in the crack exceeds the best estimate of the critical shear stress and crack width. This is consistent with the observed performance back in 1949. Node 3. What is the likelihood that an unfiltered exit exists, allowing erosion to continue? As shown in the embankment cross-section, there was no chimney or downstream filter included in the original embankment design. The random fill berms, where the leakage exits were located, were comprised primarily of shale and sandstone, which did not provide any filtering action. Therefore, there was an unfiltered exit at the time of the internal erosion incident. Node 4. What is the likelihood that a continuous stable roof forms over the crack and stable sidewalls are maintained along the crack? The impervious fill used to construct the homogeneous embankment material has an average fines content of about 70%, and the fines have some plasticity, making it virtually certain for the crack to hold a roof and stable sidewalls continuously from upstream to downstream. This is consistent with what was observed in 1949, where leakage and erosion continued until the reservoir elevation was lowered below the erosion tunnels. For nodes 5 and 6, what is the likelihood that upstream zoning fails to limit the flows into the crack, and what is the likelihood that upstream zoning fails to self-heal the crack? Both of these progression nodes require an upstream zone for flow limitation and crack filling action. As shown in the embankment cross-section, this is essentially a homogeneous embankment dam comprised of silty clays and clay silts. There are no upstream zones or facing elements that could limit flows from the reservoir to arrest erosion by reducing the hydraulic shear stresses below critical values. Similarly, there is no upstream zone that can transport particles into the cracks or developing pipes and eventually seal the filter. And if there were, there are no downstream filters or transitions to trap the eroded particles. There was a layer of riprap and bedding stone on the upstream slope, but it's thin and likely fell into the bottom of the crack. This is consistent with what was observed during the 1949 event, when there was no slowing of leakage or erosion until the reservoir was lowered below the erosion tunnels. Node 7. What is the likelihood that detection and intervention are unsuccessful? Breach was averted only because the reservoir level dropped below the entrance to the pipes. This incident was a near miss with respect to failure. After the reservoir level was lowered, the entrances to the pipes were plugged. Immediate remedial measures consisted of installing a steel sheet pile wall through the closer section of the embankment, performing extensive grouting, and installing additional upstream and downstream berms. For node 8, the last node in the event tree, what is the likelihood that the uncontrolled release of the reservoir occurs? If intervention had not been successful, Wister Dam would have almost certainly breached by gross enlargement of the leakage pipes, leading to collapse of the overlying embankment and overtopping. Fortunately, breach was averted because the reservoir was lowered below the erosion tunnels, arresting the failure mode development. Some gross enlargement likely occurred because the erosion rate was increasing even as the reservoir level was decreasing, as shown in the photos earlier in the presentation. When evaluating a potential failure mode, it is often helpful to think of more and less likely factors for each node. As shown by the tables on this slide, the more likely factors significantly outweigh the less likely factors. Soft, compressible alluvial foundation soils were left in place directly adjacent to stiff, well-compacted embankment soils, making it likely for differential settlement to occur and a transverse crack to develop. Fell et al. 2008 indicates crack widths could be substantial and in excess of 5 millimeters. Initiation of erosion is likely for best estimates of crack width and critical shear stress at higher reservoir levels above the entrance of the flaw. The embankment soils were likely dispersive, and there is no downstream filter. The primary references are provided here for more details on Wister Dam. This concludes the Wister Dam case history presentation.